So for this question, we're asked what the value of the gain controller, K, should be if the system is to have an overshoot of 5% and it's for a step input. So what we're going to try and do is get the overall transfer function for this system. So that's like C divided by R. Once we've got that, we should be able to pick out the characteristic equation, which is the denominator of our transfer function. And then once we've got that, we should be able to go through the time response characteristics and figure out what the K value needs to be to enforce this criteria of a 5% overshoot. So let's start by working out the transfer function for this system. We have a negative feedback system. So remember, the general case for this is we have some function G on the top line, some feedback function H on the bottom line, and the overall transfer function for this, which I'll call G over all, is equal to the top line, alright, that's your open transfer function, divided by 1 plus GH, where H is what's in this feedback loop. So if we look back at our example here, G is going to be the top line, so we need to multiply these two blocks together, which is going to give us 3K on S squared plus 10S plus 1. And H is the feedback loop, and for that we've just got 5. Alright, so now let's go ahead and apply this equation for the overall transfer function. And in our case, that's going to be the same as C on R. So it's going to be G on 1 plus GH. Substituting in what we've got, this is G divided by, put this in brackets, times H on the end there. Alright, so obviously this looks pretty messy at the moment with our compound fractions. So what I'm going to try and do is get a common denominator for the fraction that sits on the top line and the fraction that sits on the bottom line. And that's going to be this S squared plus 10S plus 1. So I'm going to leave the top line the same because it's already got that denominator. But for the bottom line, I need to have both terms having that same denominator. So if I want S squared plus 10S plus 1 for this term here, I'm going to have to multiply it by that expression. Alright, so top and bottom lines would cancel here, which would take us back to just having 1. So this is equal to this, and if I write this out, so 5 times 3 is 15. What I've got now is the same denominator for both terms on this bottom line. So I'm going to write this out in full, just to be clear on what's happening. So top line, nothing is happening. On the bottom line, I now have this common denominator, so I can put them together with that same denominator. Alright, so now we have this on both of our compound fractions, so they're going to end up cancelling with each other. And we're left with our transfer function just being 3K divided by S squared plus 10S plus 1 plus 15K. So this is G over all for our block diagram. So now that we've got this, we need to take out the characteristic equation, and that's just going to be the denominator of our transfer function, remembering that we need to make sure that it's normalized so we have a 1 in front of the highest power. So in our case, we've definitely got that. It's 1s squared, and the highest power of s we've got is 2, so that means it's going to be a second order system. So let's take it out. Okay, and for a second order system, we know that the general form of that characteristic equation looks like this. And remember to refer back to the videos that I did on time response if you want a reminder of that. So now what we need to do is actually go through and start equating the different constants in front of the s's together. Now, to be able to successfully solve for this K value, we can see that in this equation we've just written out, we have quite a few unknowns. We have K, we have omega n, and we have zeta. So to be able to solve, we need to kind of pre-solve for one of those values, and that's going to come from the criteria that you're given that your system needs to meet. So if we scroll back up to the top, we're told that the criteria we're aiming for is an overshoot of 5% for our system. So from that, we should be able to solve for the zeta value. So over here, I'm going to write out the equation for zeta as a function of the percentage overshoot. Alright, so that's the equation. All we need to substitute in now is the percent overshoot, for which we've got 5. So let's go ahead and do that. So it's going to be 5 on 100. And if we type that into a calculator, we get about 0.69 for the zeta value. So anytime we have this value, that means we've got a 5% overshoot. So if we come back down, what we can do is solve this based on the fact that zeta has to be equal to 0.69 if we're to meet our design criteria. So let's go ahead and start equating stuff. So obviously we have 1 equals 1 for the s squareds, which is true but not very useful to us. So we'll go with now the 10s and the s term over here. So we should be able to solve for omega n. Okay, zeta is 0.69. So we end up with an omega n of about 7.24 radians per second. So now what we can do is look at the constant terms that we have. So we've got that 1 plus 15k, all right, that's a constant, has to be equal to omega n squared on the other side here. So now that we've pre-worked omega n squared, we should be able to solve for k. All right, so subbing in, this works out to a k value of about 3.433. All right, so that means that if we scroll back up to our system, if we're able to design this block in here to be 3.44, what we should observe is an overshoot of 5%. And if we have access to MATLAB, we can actually check whether that's going to happen. So this is a little code that I wrote to be able to actually check it. So I've set up my transfer function. I've put in the k value that I'm interested in, and I've set up my open transfer function, which was just the g on the top line, and my h as well. So we need to simulate the overall transfer function's response. So that's what this line here is doing. And then I'm going to do a step input for it. And this is the result that we get out. So if you right click characteristics, you can find out what the peak response is, which is where the percent overshoot is going to be measured from. If you click on this point here, it should give you the actual values for what's happening. And we can see that we've got definitely an overshoot of 5% actually occurring, which is what we were expecting since that's what we designed for. So definitely we've got the right solution here. So that's all there is for this video, and I'll see you in another one.